Hello everyone, I'm Luo Wenkan from Shanghai Jiao Tong University. I'm going to talk about our work. When you watch a video on the internet, we all have this annoying experience. The video suddenly gets stuck and starts rebuffering. Adaptive video streaming is a popular solution to address this issue. In other words, it aims to improve the video quality and reduce the rebuffering time. We consider a typical adaptive video stream system, where a original video is temporarily divided into multiple chunks at the server, as shown in the right. Each chunk has a fixed time duration and is further encoded into several quality versions with different bitrates. As a client, shown in the left, adaptive bitrate algorithm will choose the best bitrate from these available versions for each chunk, so as to maximize the user's QoE under the limited network throughput. Here, we will focus on designing an ABR algorithm for the bitrate adaptation. There are two challenges in designing a good adaptive bitrate algorithm. One is the uncertain throughput dynamics. For example, at this point, how would the future throughput look like? It goes higher, or it could remain steady for a while and then drop. In fact, it can be one of the many possibilities. So past throughput observations cannot accurately predict what will happen in the future. It is very challenging to select a bitrate that adapts to the real throughput. Another problem is that the throughput distribution varies in the real world. For example, when we switch from a 4G signal to a 3G signal, or when we walk into the toilet, the throughput distribution that we experienced will change a lot. While most ABR algorithms based on the throughput prediction struggle to generalize to a wide range of network environments or distributions, especially for data-driven methods. In this paper, we propose a BNN-based robust ABR algorithm that is BayesMPC with a model predictive control-based rate adaptation framework. We aim to achieve both superior and robust QoE performance for adaptive video streaming. First, we adopt a BNN-based model to improve the prediction accuracy of the network throughput and capture their prediction uncertainty. Second, by using the prediction results, the uncertainty-aware robust MPC strategy is then proposed to improve the robustness of the bitrate adaptation. The uncertainty measurement of the future prediction at each step can tell us how confident the prediction is, which can significantly reduce the risk of rebuffering events. Third, we implement BayesMPC for adaptive video stream on 3 real-world network traces datasets. And the results show that BayesMPC outperforms the overall QoE performance and the generalization performance across a wide range of network and use conditions. And before we talk about BayesMPC, let's first look at the preview schemes. In general, existing ABR algorithms can be classified into two categories: classic control theory based and the machine learning based. The first categories pick the bitrate based on the predictive future throughput and buffer occupancy. Because of the challenges of throughput prediction, they always cannot achieve a good performance in practice. In contrast, recently proposed machine learning-based schemes can achieve outstanding performance, especially the deep reinforcement learning based, for example, Pencil from Silicon 2070. They always directly learn a good ABI policy from the experiences and the experiences is historic. However, some drawback of these algorithms can be found in comparison to others. For example, they can only perform well in a specific domain, since the neural network weights can hardly generalize to a new environment that differs from the training data. In fact, classic control theory-based ABR algorithms can always achieve a stable performance in practice, and the prediction accuracy of the dynamics, such as the network throughput, is a critical ingredient for improving the performance of these algorithms. Because even a small prediction bias can influence the user's QoE or not. However, as we said before, it is very hard to learn an accurate dynamic model for the prediction. And there are a lot of noises in the network transmission, and a video client can hardly get enough network information from the streaming processes. So it is challenging to predict the stochastic future network throughput. We call it the anionic uncertainty. In order to capture the anionic uncertainty, a probability distribution of users' network throughput, rather than a single deterministic value point, should be considered at each step. Moreover, we also should consider the epistemic uncertainty. This type of uncertainty corresponds to subjective uncertainty about the dynamics function. Because we don't have enough data to determine the underlying system exactly. If we have infinite training data, the epistemic uncertainty should vanish, but you know it is impractical. Therefore, in order to make a reliable prediction, we want to jointly consider the anionic and epistemic uncertainties during model prediction. We assume that the noise introduced in the throughput measurement follow the Gaussian distribution. A probability distribution rather than a point estimate will be used to measure the anionic uncertainty. In addition, we can measure the epistemic uncertainty by Bayesian neural network, which introduced the stochasticity to the neural network weights. The main difference between the normal neural network and the Bayesian neural network is, in the normal neural network, the weights are all fixed value, while the weights of BNN are all stamped from a learned probability distribution. We call it post-theorem distribution. The stochasticity of weights enables the BNN-based predictor to be aware of the epistemic uncertainty. Therefore, we can predict the future throughput by using the BNN-based predictor. Based on the Bayesian inference, specifically, given a set of training data, DM, the predictive distribution of a future throughput can be given based on the past throughput. The Bayesian post-theorem of the weight W can be calculated by the Bayesian rule, with PW is the prior distribution and Py conditioned on X and W is the likelihood function. The true Bayesian post-theorem is always intractable in practice. So we can calculate the post-theorem by finding a variational approximation which learns a new distribution QW condition under theta to replace the true post-theorem. In addition, we have shown in the paper that by using the negative log-likelihood loss function to train this BNN-based predictor, the generalization error can be minimized with the guarantee of Bayesian theorem. And let's talk about the red adaptation framework. As we said before, it is impossible to accurately predict the throughput value, but we can capture the uncertainties of the prediction. With the uncertainty, we build a confident region, which means that we can guarantee that the true average throughput of case video chunk is contained in the confidence region with a probability of at least 1 minus delta. Then we can use the lower bound of this confidence region as the predicted worst case throughput value and use the MPC strategy to maximize the worst case user QoE. So this objective function will get a conservative MPC strategy that managed to find a control sequence such that no rebuffering events will happen in the future. This is the system framework of BayesMPC. The left part is the video server and the video client. The right part is the proposed bitrate adaptation module. Now we will show you the experiments that we did. First, we compare BayesMPC with some point estimate method and found that our proposed BNN-based predictor can improve the QoE indeed. And we show the confidence region of BayesMPC during the throughput prediction. And we can see that a confidence region of the throughput prediction, which shown in the shadow, can be measured with a high accuracy. And it should be noted that there is a trade-off between the QoE degradation and the rebuffering risk reduction when we choose the value of Z data. And we found that it performs best when Z data equals 1.5. So we use this value for confidence region in the following experiments. Then we compared BayesMPC with baseline ABR algorithms in terms of the QoE performance in various user or network conditions and different QoE metrics. We found that BayesMPC performs more superior on FCC data traces. The performance gain of BayesMPC over other baseline algorithms increased to at least 9%. And in these experiments, we want to explore the generalization performance of BayesMPC under an unseen network condition. We evaluate the different ABR algorithms on the traces of Ober. None of these Ober test traces has been experienced during the training process of BayesMPC and Pensive. It can be found that BayesMPC still performs best in the traces of Ober, although the performance gain of other baselines is narrow. While Pensive performs worse than robust MPC in some traces. So we can see that BayesMPC is always optimal in Obol, but Pensive is not. As a summary, BayesMPC is a system that uses Bayesian neural network to predict network throughput and measure the prediction uncertainties. It robustly optimizes the bitrate with these uncertainties, and it outperforms the existing approaches across a wide range of network conditions and QoE preference. More information and open source code can be found in our website. With that, thank you. I'm happy to take questions.